Imagine a truck that, the more it travels, the more money it puts in the pockets of its operator. It sounds like an exaggeration, but that's exactly the logic behind the Tesla Semi. And the numbers that are about to be revealed will leave many people speechless. In the second half of 2026, when large-scale production finally gains traction, the freight transport market will face a reality that few anticipated: an electric truck that transforms every kilometer driven into a concrete, measurable, and, above all, sustainable financial advantage. What once seemed like a distant promise is beginning to show itself as the quietest and at the same time most powerful change that the logistics sector has seen in decades. And it all starts with a detail that seems simple, but carries enormous weight when you think about scale: the cost per mile. While a conventional diesel truck consumes an average of 80.5 cents per mile just to keep its wheels turning, the Tesla Semi operates at around 23 cents per mile. This number didn't come from a laboratory simulation or an optimistic projection made by engineers in an office. It comes from real data collected in concrete operations by companies that have already put the Semi to work on fixed, high-demand routes. The average consumption recorded was approximately 1.64 kilowatts per mile, and with commercial electricity rates hovering around 14 cents per kilowatt, the numbers add up quite favorably for those operating the machine. The difference compared to diesel is not small. It's a gap that separates two completely distinct business models. To understand the real impact of this, simply consider what happens over a year of operation. A typical heavy truck travels more than 100,000 miles per year on commercial routes. Based on this calculation, the cost difference between a semi-electric truck and an equivalent diesel truck exceeds $40,000 annually per vehicle. Now multiply that value by a fleet of 10 trucks, and the result begins to have a weight that no CFO can ignore. This is not a marginal saving, the kind that discreetly appears on the balance sheet at the end of the quarter. This is a structural transformation in the cost structure of any logistics operation that decides to make this transition. But if the energy cost is already surprisingly low, there's a very precise technical reason behind it, and it begins long before the truck even starts its engines. When talking about energy efficiency in heavy vehicles, most people immediately think of larger batteries or more powerful engines. What few imagine is that one of the Tesla Semi's greatest secrets is hidden in its shape, in the way it was sculpted to cut through the air, with a precision that until now was exclusive to the most exotic cars on the planet. And that's no exaggeration. The Semi's aerodynamic drag coefficient, confirmed at 0.4, puts this 40-ton truck on the same level as a Bugatti Veyron, one of the most refined supercars ever built by the global automotive industry. This comparison alone says a lot about the level of engineering involved in the project. To understand why this matters so much, it's necessary to understand what air resistance does to a moving vehicle. At highway speeds, which is precisely where trucks spend most of their time, aerodynamic resistance is responsible for consuming between 50 and 60% of all the energy used by the vehicle. This means that more than half of the fuel or electricity used on a long trip is simply being used to push air aside. A conventional diesel truck, with its high cab, square trailer, and structure developed without much aerodynamic consideration, has drag coefficients ranging from 0.6 to 0.8. This difference, which seems small in numerical terms, represents in practice a much greater energy expenditure to travel the same distance. The Tesla Semi was designed from the ground up with this variable as an absolute priority. Unlike competitors who attempted to electrify existing diesel platforms, the Semi was born as a completely new project, where every curve of the body, every detail of the cabin, and every inch of the structure was designed to minimize air friction. The result is a silhouette that defies common sense about what a truck should look like. The centralized cabin, the tapered nose, the smooth transition between the cabin and the trailer, and the absence of unnecessary elements in the external structure all contribute directly to this extraordinary number. With less drag, the Semi needs less energy to maintain the same speed, which extends its range and passively reduces the cost per mile, simply through the vehicle's geometry. All this aerodynamic efficiency, however, would be far less impressive if the Semi wasted energy during one of the most common moments in the operation of a heavy truck: braking. Anyone who has ever seen a truck descending a mountain or braking in a busy urban traffic area knows that this process, in conventional vehicles, is pure waste. The heat generated by the brake pads pressing against the discs represents energy that was consumed by the engine, transported for kilometers, and simply released into the air without any use. In a diesel truck, this is unavoidable. The braking system exists exclusively to dissipate kinetic energy, and the heavier the load and the more frequent the braking, the greater the waste, and the faster the wear and tear on the components. It's an equation that the transport sector has learned to live with, but has never been able to solve until now. The Tesla Semi addresses this problem in a way that completely transforms the logic of waste. The vehicle's regenerative braking system works almost intuitively. The moment the driver slows down or the truck begins to descend a ramp, the electric motors reverse their function and start operating as generators. Instead of consuming electricity to move the vehicle, they convert the truck's movement into electricity and send that energy back to the battery. The process happens automatically, smoothly, and completely transparently to the driver, who simply perceives that the vehicle decelerates naturally, without the brake pads needing to be used in most situations. What was previously discarded as heat now returns to the system as fuel. The recovery rate of this process is one of the most surprising features of the Semi. Between 70 and 80% of the energy that would be lost during braking is recovered and returned to the battery. In an operation with routes that include ascents and descents, braking in urban areas, or frequent stops at distribution centers, this percentage translates into a real and measurable extension of the vehicle's range. This means that, at the end of a journey with a lot of braking, the Semi arrives with a more charged battery than it would without this system. For fleet managers operating in regions with varied topography or on routes that cross dense metropolitan areas, this feature can be the difference between completing a route with a comfortable charge margin or needing an extra stop to recharge. If there's one objection that always comes up when the topic is electric trucks, it has a very simple name: charging time. The image that comes to mind for any fleet manager is that of a vehicle stopped for hours at a charging point while the competition passes by on the highway with their diesel trucks refueled in 10 minutes. This concern is legitimate, and for a long time, it was one of the strongest arguments against the adoption of electric vehicles in heavy cargo transport. What changes in the second half of 2026, however, is that this objection begins to lose strength in a way that few expected. Not because the problem was ignored, but because it was solved with engineering that goes far beyond what the market had as a reference until now. And the solution has a name: Megacharger. The charging network, developed specifically for the Tesla Semi, operates at a peak power of up to 1.2 megawatts. To get an idea of what this number represents in practice, simply compare it to the chargers available for other electric trucks on the market, which generally operate between 250 and 350 kilowatts. The Megacharger delivers 4 to 5 times more power than these systems, completely transforming the downtime equation. With this capacity, the Semi can recover approximately 60% of its battery in just 30 minutes of connection. Considering that the vehicle's battery has an estimated capacity between 850 and 900 kWh, this charging rate in such a short time represents an engineering feat that is still unparalleled in the heavy vehicle segment. What makes this data even more relevant is the regulatory context in which trucks operate in the United States. Traffic laws require drivers of commercial vehicles to take a mandatory break of at least 30 minutes after a certain number of hours of continuous driving. This break, which in diesel vehicles is merely an unproductive interval, becomes a recharging window in the Semi, replenishing a significant portion of the vehicle's range. In practice, this means that the Semi can operate almost continuously, respecting the legal requirements for driver rest while maintaining the battery at operational levels suitable for the rest of the route. Time that was previously lost is now used strategically, without any additional cost to the operation. Fast charging and low fuel consumption would already be enough to grab the attention of any fleet manager, even slightly attentive to the numbers. But there's a dimension to the Tesla Semi that goes beyond day-to-day efficiency and completely changes how you should think about buying this vehicle. It's not about lower operating costs per mile, nor about a surprising charging time. It's about something much more fundamental: how long this truck will last. And when that number is revealed, it completely redefines the concept of investment in the freight transport sector. The 4680 battery technology, developed and produced by Tesla itself at the Gigafactory Nevada, was designed with a goal that sounds almost absurd to those accustomed to the life cycles of conventional diesel engines. The target is 1 million miles of useful life. It's not an optimistic estimate. It's the engineering parameter upon which the entire vehicle was built. To understand the significance of this number, it's important to consider what happens to a diesel truck over time. A high-quality diesel engine, well-maintained and operated under ideal conditions, generally begins to require major overhauls or complete replacement between 300,000 and 500,000 miles of use. This point marks a significant financial turning point for the operator. Either they invest in an expensive engine overhaul, or they scrap the vehicle and buy a new one, restarting the entire depreciation cycle and initial costs. In either case, the truck becomes a liability at the very moment it should still be generating revenue. The Semi, with its electrical architecture and 4680 battery, was designed to continue operating reliably well beyond the point where any diesel would begin to show signs of structural fatigue. The reason this longevity is possible is directly linked to the vehicle's mechanical simplicity. A diesel engine is an internal combustion system with hundreds of moving parts that operate under extreme temperature and pressure conditions throughout its lifespan. Pistons, valves, belts, pumps, cooling systems, multi-speed transmissions, exhaust systems with emissions treatment. Each of these components is a potential point of failure, and each failure represents downtime and money spent. The Semi replaces all this complexity with electric motors with very few moving parts, no conventional transmission, no exhaust system, and none of the fluids that need to be changed regularly in a diesel. The direct result of this simplicity is an operational availability rate of up to 95%, meaning the truck is on the road generating revenue almost all the time. A vehicle that lasts 1 million miles, operates with 95% availability, and consumes less than half the energy of a diesel inevitably raises a question any CFO would ask before signing any purchase order. How much does all this cost? And when the number appears, the initial reaction of much of the market is hesitation. The price of the Tesla Semi in its long-range version is around $290,000, a figure that represents approximately double the value of a standard cab diesel truck, which is usually traded between $120,000 and $150,000. Looking only at this isolated number, without any additional context, it is understandable that the immediate instinct is to back away. But it is precisely at this point that superficial analysis begins to betray those who perform it, because the purchase price of a commercial vehicle should never be read outside the context of the total cost of operation over its useful life. The price difference between the Semi and an equivalent diesel vehicle is around $150,000. This is the amount that needs to be recovered for the investment to start generating a net return. With annual savings of approximately $40,000 in energy costs alone, plus a reduction of at least 50% in preventive and corrective maintenance expenses, the total annual savings per vehicle approaches $50,000 to $60,000, depending on the operating profile. Putting these numbers on a simple timeline, the break-even point between the initial investment and accumulated savings is reached in approximately 3.5 to 4 years of operation. From that point on, every mile driven by the Semi represents a profit that a diesel vehicle on the same route simply cannot generate because its operating costs are structurally higher, and there is no variable that can change that within the internal combustion model. What makes this scenario even more accelerated in certain regions is the existence of government incentive programs that significantly reduce the initial outlay. In California, for example, the HVIP program offers subsidies of up to $120,000 per zero-emission truck purchased by operators who meet the eligibility criteria. With this incentive applied, the effective price of the semi-truck drops to approximately $170,000, which puts it only $20,000 to $30,000 above the price of a conventional diesel truck. In this scenario, the break-even point is no longer measured in years, but in months. In high-mileage operations on fixed routes, this break-even point can be reached in less than a year of operation, transforming what seemed like a bold investment into a practically obvious financial decision for those who have access to these incentives. All these financial, technical, and operational advantages that the Tesla Semi brings would have a much more impact on the market if production kept pace with demand. And this is where the conversation needs to be honest, because there is a considerable gap between what has been announced and what industry experts consider feasible for the second half of 2026. The official goal is ambitious: 50,000 units produced this year. To get an idea of what this number represents, just consider that the American Class 8 truck market moves around 245,000 units per year in total. Reaching 50,000 semis in a single year of production would mean conquering almost 20% of that market at once, with a product that is still in the early stages of its large-scale production line. It's a claim that requires much more than goodwill to become a reality. The production line installed inside the Gigafactory Nevada is already operational, and available images of the factory interior show a highly automated environment covering a significant area of the complex. This is a positive and concrete sign that the project has moved from the drawing board to a real industrial execution phase. However, the history of the Semi itself serves as an important reminder of the difference between intention and delivery. The vehicle was originally announced with a production forecast for 2019, then for 2020, then for 2022, and subsequently for 2024, before finally beginning limited deliveries. Each of these delays had concrete reasons, ranging from challenges in battery development to bottlenecks in the supply chain. And none of them were simply the result of negligence or lack of commitment to the project. The main obstacle to rapidly scaling up production remains the same as always: the battery. The Semi uses a battery pack with an estimated capacity between 850 and 900 kWh. Composed of 4,680 cells, the Tesla is still scaling up in Nevada. Producing batteries at this scale, with this level of capacity per vehicle, requires a volume of cells that puts direct pressure on a production line that simultaneously needs to supply other models of the company. Each Semi consumes approximately 14 times more cells than a Model Y, which means that each unit of the truck has a huge impact on the company's total battery production capacity. This bottleneck is not insurmountable, but it is real, and it will take time to resolve structurally.